Continuing on the subject of capacitance, if I remember correctly, and such. Yes, sort of redoing Professor Lewin a little bit.
All right, let's get this down, and I'll bring the lights back up, and we go back to normal.
Okay.
I have here a 100 microfarad capacitor. It's a dangerous baby. And we can charge that up to 3000 volts. And when we do that, we get 0.3 of a coulomb of charge on that capacitor. So I'll give you some numbers. So it is 100 microfarad. I'm going to put a potential difference over it of 3000 volts. That gives it a charge Q of 0.3 coulomb, and that means that 1/2 CV squared, which is the energy that is stored then in the capacitor, is 450 joules. And this
it'd be kind of nice to be able to see inside of it or something, have a diagram of it, something, just so we know how it works. But alas, I do not believe we will be given that.
will take 15 minutes. And so I'm going to charge it now, because at the end of the lecture, I need a charge capacitor for a demonstration. And so I can show you there the potential difference over the capacitor, which will slowly change. And we'll keep an eye on it during the lecture. And then by the time it's fully charged, we will have reached the end of the lecture, and then we can continue. So here is then this monster, the 100 microfarad. I call it a monster because the amount of energy that you can pump in there is frightening. It's 450 joules. And my power supply is here. That would deliver comfortably the 3000 volts. In fact, this is the voltage of the power supply. This is about 3800 volts. And so
Probably be good to know how much it can put out in terms of watts, instead of all this joules stuff.
So now the idea is that I'm going to charge this capacitor. Always have to be very slow and careful that I don't make mistakes, because this is really a device that could be lethal if you are not careful. So I think we're okay. The moment that I'm going to charge this capacitor, the reading there will show you the potential difference over these plates, and it will take a long time for that to go up to 3000 volts. And so I think I'm ready to go.
It only takes as long as your power supply can pump it in, so it's the weakness of the power supply that decides how long it takes. But, that's sort of obvious.
And I'm going to charge it now. So you see now that the potential difference over the plates is very low, it's near zero. But if you wait just a few seconds, you will see very slowly that it is charging up. And 15 minutes from now, we will be very close to the 3000 volt mark. And then we will return to this. So we'll leave it on just for now while it is charging. The idea of a photo flash is that you charge up a capacitor and that you discharge it over a light source. So the idea being that you have a capacitor, let me erase some of this, and then we charge the capacitor up, put a certain amount of energy in there, and then we dump all that energy in a bulb. So here's the capacitor, we're going to charge it up, we have a switch here, and here is a light bulb, and when we throw the switch, then all the energy will be going to the light bulb. If this is positively charged and this is negatively charged, the current will...
It is kind of a weird dichotomy, a contradiction that, some of these, you have this very obtuse mathematics going very quickly, blah, 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 I do the integral of this, dt times blah, 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 very fast. And then you'll spend all this time on something so rudimentary that, it's like, yeah, okay, I probably learned some of this stuff in 5th grade. Well, at least I did, on my own anyway.
Start to flow, and you will see a flash of light. I have here a capacitance of 1000 microfarads. So C equals 1000 microfarads. I'm going to put a potential difference over that capacitor of 100 volts, which then gives me a energy of 1/2 CV squared, which is 5 joules. In fact, this is not just one capacitor, but these are 12 capacitors, which I hooked up in such a way that the 12 capacitors of 80 microfarad each are a combined capacitor of 1000 microfarads. And so I'm going to charge it up, and then I'm going to discharge the capacitor through the light, and then you will be able to see some light, perhaps, depending upon how much energy we dump through there. So concentrate now on this light bulb. The 100 volts, you should see here. Do you see it? So it's set at 100 volts now. And I'm now going to charge it in a moment.
Seems to be a lot easier just to use a regular 12 volt kind of, even a 3 volt, there's so many flash units that are so cheap. Why bother with this light bulb stuff?
When that I charge, you will see the voltage over the capacitor. And so it takes a while for it to charge up, so it goes very down to 0 and then slowly comes back to 100. It may take 5 or 10 seconds. So if you're ready, then there we go. Took only 5 or 6 seconds. And so now we have 100 volts, so we have 5 joules stored in there. And I'm going to discharge that now over this light bulb. If you're ready, 3, 2, 1, 0. A little bit of light. I can tell that you're disappointed. It's not very exciting. It's not really my style, is it? Well, what we can do, we can increase the voltage a little bit. We could go to 250 volts, in which case, since it goes with V squared, we would have 6 times more energy, so then we have 30 joules. So let's see whether that's a little bit more exciting. So now I have to jack up the voltage to 200.
Okay, so 30 joules. Now the big thing that takes 15 minutes to charge is only 400 joules. And this is 30, and it only takes about 10 seconds to charge up to 250 volts. I mean, it does seem like you'd be better off making a few of these instead of that one big thing. Yeah, I'd buy 6 of these setups and just forget about the big thing.
50 volts. Now you see the power supply again. 250 volts. We're getting there. We don't have. Oh boy, am I lucky on the button. So 250 volts.
Let's
and
see
now
how
I
long
can
it
charge
takes.
up again. It will take a little longer.
See how
so
long
you
it
see
takes.
the voltage over
1,
the capacitor.
2, 3,
140,
4,
170,
5,
200,
6, 7,
250. There we are.
7.
And now we
7
can see
seconds.
whether we get a little bit more light.
So it takes 7 seconds to get 30 joules. 7 seconds, 30. So why is he using the big thing? Obviously, these little ones are more efficient per weight.
We go from 5 joules now to 30 joules. 3, 2, 1, 0. Ah, now we're getting somewhere. Now you really see how a photo flash works. Now, we all, of course, have destructive instincts. And so you wonder, right? You're thinking the same thing that I do. Shall we try 340 volts and see whether the bulb maybe explodes? I don't know how high this voltage supply can go. Let's see. Let's go all the way.
Yeah, I think he knows how high it goes.
337 volts. Okay, so that would mean that we have 50 joules roughly. It goes as the voltage square. Well, let's charge again.
1, 2,
charging
3,
now.
4, 5, 6,
200,
7, 8, 9,
280,
10, 11,
300.
12, 13.
There we go, 337
13
volts.
seconds.
Now let's see. Ah, we did it!
And he probably had, whatever, 50 or 60 joules on there, so he had, 1/10 of the other thing in a mere seconds. So 10 times 12 seconds, he could charge this whole thing in 2 minutes versus the 400 joules at 15 minutes. Just saying.
Broke!
So it's nice that he does the, like I said, I like that he does experiments. Some of them are very insightful, very good. But yes, some of it is Barney the Dinosaur as far as I'm concerned. A little bit too, you forgot you're in college. I mean, sometimes he says, this is an MIT equation or something. This is an MIT, and, sometimes it doesn't look like MIT. It looks like Sesame Street.
I have a photo flash. And I have the photo flash here. And this photo flash has a capacitor of about 5,000 microfarads, real biggie. And we can charge that up to a potential difference of 100 volts. Even though the battery is in there, only 6 volts, there's a circuit in there, we'll learn about that later, which converts the 6 volts to 100 volts. And so we can charge up this capacitor to 100 volts. And that means that the 1/2 CV squared, the energy stored then in that capacitor, will be 25 joules. And I can dump that energy.
So 25 joules, you know, again, compared to 400, and the flash takes us 2 seconds to charge.
With the light bulb, and then we see a bright flash of light.
From friggin' little batteries, 6-volt batteries. How many joules are in the batteries to start with? I mean, really, all you're doing with a capacitor is saying I can put a lot of, I can take the capacity of a battery and I can put it over time and put it in a capacitor, and the capacitor can deliver what the batteries couldn't in a quicker amount of time. So that's one of the uses of capacitors. Obviously, it'd be good to just try to make capacitor batteries, but apparently they're just too expensive still.
Light, because this discharge can occur in something like only a millisecond. So you get a tremendous amount of light only for that millisecond.
I mean, the problem is the capacitor doesn't deliver the voltage consistently. And it doesn't deliver the current, the wattage, at a consistent voltage. So as it's losing voltage, as it's losing joules, it starts dropping the voltage, which isn't very helpful.
And I want to demonstrate that to you. And the only way I can demonstrate that to you is by aiming this flashlight at you. I don't want to damage your eyes, so I warn you in advance.
Well, look, this is just so corny. I warn you in advance that flash bulbs go flashy. So what are you supposed to do? Close your eyes and turn your head? No, obviously it's made to be shot at people. Obviously. You wouldn't be able to take very good pictures if everybody just goes like this. But okay. Sorry, I'm being a little critical. But this is a little bit... this isn't very MIT.
So I am charging up now my capacitor. It will take a while, and I'm going to take your picture. I might as well. But it's going to be very dark in the back there. And so I've asked Marcos and Bill to also have some flashlights, which go off at the same time that my flashlight goes off. Now you may say, well, how can you do that? Because
it's not really a flashlight, it's a flash bulb, but okay, I guess that's a, whatever that is, over there people thing.
If this flash only lasts a millisecond, how can you synchronize that? Well, the way that's done is that those flashlights are waiting for my light signal to reach them. And that goes with the speed of light. It takes way less than a millisecond to get there. And they go at the same time that they receive.
Yes, the way less than a millisecond, but it's still, you still have to wait for the light to get to them, and then they have to process it and say, yes, I saw the light, and then they have to do a little bit of electronics to say, yes, flash. So they are going to be a tiny bit behind. It's just not enough to worry about.
My light flash. And so we call them flash assists. And so let's see whether we can do this. I have a green light here. That means I can take my picture. And yeah, oh, you don't have to comb your hair, but you're looking good. Okay, let me focus because that's important. So make sure you see the flash. You ready for this? Did you see the flash?
It was almost like this was made in 1982 or something. It was made in 2009 or something. There were digital cameras and all that kind of stuff. It's obviously using a film camera. A little bit funny.
Did it flash? Oh, it did. Oh, you can say yes. So, did the light assist also flash? Okay, but you haven't seen that yet, right?
Or would you have your eyes closed when you're... I don't know.
Because you were looking at them. You should have looked... You really should have looked at me. So why don't we take a picture, Marcos, Bill, aim the flash assist at the students here, and then we'll try it again.
Exciting.
You ready?
Very exciting.
Oh boy. Why don't you say cheese for a change? Okay, look at me. Oh boy, you're looking great. You really, you're out of focus. There's one person sleeping there. Oh, we'll let him sleep. That's okay. Did that work? Did you see the flash? You did, eh? 25 joules. But those haven't seen it yet. So Marcos, Bill, make sure that we go this way and give them a chance to see this light flash. So we get a little bit of assistance there, the lights.
So you can imagine that he could probably flash that at least 6 times, 7 times a minute. let's say 10 times a minute, 10 seconds to charge. At 25 joules, that's 250 joules a minute. So in 2 minutes, he can do 500 joules. And that capacitor's taking 15 minutes to charge. He's only doing 400. Just saying.
And let's see how this works. Make sure that you see the flash. Very good. You can going to see another 25 joules going through this light bulb. Very good. Oh.
I mean, obviously, having a capacitor can do 3,000 volts is, that's useful when you need 3,000 volts. But, it's really not a very good demonstration of anything other than, obviously, if you have a high voltage capacitor, it's obviously harder to charge, apparently. And because you have to put so much high voltage into it, and it's hard to have a high amperage 3,000 volt power supply, I guess. And the other thing would be, what other problem would there be? Obviously the capacity can't be that great. If you're holding that much voltage, the plates have to be kind of far apart to prevent sparks.
Oh, yeah. Your hand is in front of your mouth, sir. Yeah, that's okay. Thank you. Very good. Did you see the flash?
So it seemed like kind of a waste of time and space there. Waste of bent space.
Did the assist go? So that's the idea of photo flashes.
So yes, it has absolutely nothing to do with capacitance. It's just entirely unrelated and not very interesting.
So you dump a lot of energy in a very short amount of time, and you get a very bright flash. Professor Edgerton at MIT became very famous for his flash.
See, he's already demonstrated all of this 3 times now, and he's probably going to do a 4th demonstration of exactly the same thing. But anyway.
Flashlights. He invented flashes that can handle way more energy than this flash, and they can dump that energy in less than 1 microsecond. And so this opened up the road to high-speed photography, and that made it possible to study the motion of objects on timescales of microseconds and even shorter than that. And I'd like to show you some of the pictures that were taken with Doc Edgerton flashes. The first slide. You see a bullet coming from the right, going for a light bulb. The exposure of this...
Well, you can tell it's from like 1950. So it's a ceramic bulb holder. But anyway, so what? Yeah. Okay, so that's the last time MIT did anything interesting with strobes.
Picture is only 1/3 of a microsecond, during which the bullet probably moved only 1/3 of a millimeter, so it looked like it's completely standing still. And the bulb is heading for disaster, but it doesn't know that yet. The bullet moves in 100 microseconds, about 8 centimeters. And the next picture is taken 100 microseconds later. Again, 1/3 of a microsecond's exposure. So if we can look at that, there you see. So the bullet now just penetrates the light bulb. And then the next picture is another 100 microseconds later. And there you see the bullet emerging from the light bulb. And this light bulb has hardly realized that it is broken.
Pretty much the same as the Apple picture I've seen. So, yes. Let's just shoot stuff.
But it's beginning to dawn on it. And then the next slide is one wonderful picture of a boy who's popping a balloon. And you see half the balloon doesn't even...
I mean, it's like obviously like chroma color photo. I mean, it's just obviously some kind of 60s picture.
Know yet that it is broken. Doc Edgerton also developed a lot of strobes. A strobe, I have one here, is an instrument that repeatedly discharges energy over a light bulb, and so you get repeated flashes, and that then gives you an instrument like this. You've seen them in use. They are being used.
It is sort of interesting because of the bad frame rate that the whole thing just changes entirely, because the frame rate is too low.
At airplanes, just for warning signals, and you've also seen them on tall towers near airports, also warning signals, but there are a lot of more things you can do with strobes. And later in 802, I will show you, for instance, that you can measure the rotation rate of motors with flashlights, with these stroboscopes. And motors are going to play a more important role in 802 than you may have guessed before you took this course. You can also measure with strobes the rotation, the speed of your record player if you still have one, and then you can adjust it so that it just has the right speed that is required. So there are a lot of things you can do with strobes, and some of which we will see also in 802.
So again, kind of off the subject of capacitor.
So now I return to my capacitor there. And let's see how it is doing. Oh boy, we're close to the 3000, which was my goal. It takes, you see, a good 15 minutes to actually reach the 3000 volts on this huge capacitor and to get in there the energy, the 450 joules that I wanted. And why is it that
So again, only 450 joules, all of that. The flash bulb did it in 3 minutes. It does 450 joules.
I want to show you this? Well, I want you to appreciate the idea of a fuse. You have lots of fuses at home. The fuse is a safety device. A fuse is something that melts, something that breaks, if the current that you are using is too high. Suppose you have a short, electric short without realizing it, in your desk lamp, and a very high current would start to flow, then the fuse will say, sorry, you can't do that, the fuse will melt.
I think a fuse will melt based on the wattage, essentially. I mean, it's more than just current because it's your voltage also. So that if the voltage goes too high, there's some fuses that are voltage sensitive, I think. Maybe I'm wrong. Maybe they all are melting. Just trying to think off the top of my head. I guess you would have a spark detector that would be the fuse. So it would check the gap. There would be a gap, and if the gap sparks, then it flips the fuse.
And then that prevents you from a disaster, which actually might give you a fire. And we already showed, in a way, the idea of a fuse, because when we broke this light bulb, that was, in a way, a fuse. We dumped too much energy through that light bulb, and so the light bulb itself was already like a fuse.
See, I think it'd be a lot more instructive if maybe as a supplement to these courses, they just took common stuff, and take it apart and just show you like a circuit breaker, which is a reusable fuse, and just explained how it worked. Yeah, I think that would be a good supplement, to have maybe an hour or two of content that just explains some basic hardware and how it works.
This is really more like a fuse that we are used to. It is we have a wire there, which is an iron wire, which is 12 inches long, and it has a thickness of 30 thousandths of an inch.
Which doesn't, 30,000th of an inch is pretty thin, right? 30 thousandths, I have to figure out how many millimeters that is. It's probably a millimeter, right? I don't know, 30 thousandths. 30 thousandths. So it's 1/30,000th of an inch? I mean, that'd be an incredibly thin wire. It's much thicker than that.
And we're going to dump the 450 joules through that wire. So the idea is very much like we had the photo flash. We have all this energy in the capacitor. And
yeah, well, let me see the wire. There's no way that wire's that thin. 30,000th of an inch is like a little bit thicker than a hair or something.
Instead of dumping it through the light bulb, which was this system, we now have here a wire. And when I throw this switch, the energy will go to the wire. And chances are that you may see the wire glowing a little bit, and then it would melt, and that would then give you the idea of a fuse. And it's also possible that after we've done that there may still be energy left on this capacitor. And I can show that to you too then, because I can short out the two ends of the capacitor and see whether we still see some sparks, which would indicate that...
Yes, well, you could have done that with the other thing, where you still have capacitance on those little capacitors where you blew out the light bulb, because it was quite obvious you blew up the light bulb before it produced much light, so there's probably, those capacitors still have half their capacitance is still there, probably.
There's still some energy left. So if you are ready, I'm always a little bit scared with this demonstration, not so much about what's going to happen. That thing will probably just melt and maybe we see a little bit of light. That's not the issue, but I'm afraid of this baby because that has now a tremendous amount of energy. So I stopped the charging. So let's do that. And if you're ready,
Oh, look
then
at
I will
that
try
thing.
to
It's
dump all the
huge. It's just big, thick. It's a big, thick piece of wire. It's not a little. It's not 1/30,000th of an inch. It's a 30,000th of a meter. Anyway, I know it's just a typo, but I mean, come on. 30,000th of an inch. It's 1/3 of an inch. It's like 3/8 of an inch.
energy through this wire. 3, 2, 1, 0.
Well, I guess it was because this thing didn't go anywhere, so the wire must be inside of whatever that thing is. So who knows what kind of wire it was. But it just seems to me blowing up a wire that thin would be really easy to do.
This is the way a fuse works. This is very effective, as you see. And if you hear this happening in your basement, then, well,
Well, it's not exactly how a fuse works because they melt slower than that, but whatever. I mean, they don't blow up because you're seldom abusing a system that aggressively.
maybe that's a fuse. We can now check whether there's energy left on that capacitor. Maybe not very much, but it's unlikely that everything was dumped in the iron, so let's see whether there's some left. So I'm going to short it out with this conducting bar and see whether we can get a spark. And we can. So there's still some energy left. Okay, see you Friday.
All right, well, that was a disappointing bit of mushy, the ending here. So anyway, anything I gotta say? I don't think so. Let's see, is there something I could draw? I have new drawing capacity. Watch this. Look at that. Pretty cool, huh? Yeah. Alright, anyway. Yeah, I don't have anything to draw, I don't think. Capacitor is a capacitor is a capacitor is a capacitor. Mostly, kind of. And we sort of already went over some of that, so. Alright, so we'll call it a video. And so till the next edition, thank you for your attention and whatnot.